Alkanes undergo reactions called eliminations, where two groups are lost from the substrate and a pi bond is formed. One type of elimination reaction is the E2 reaction. It differs from the E1 reaction because it occurs in the presence of a strong base and it takes place in one concerted step. The strong base, displayed in red, attacks a hydrogen atom that is vicinal to the leaving group. In the transition state, the pi bond forms. This happens at the same time that the bonds from carbon to hydrogen and from carbon to the leaving group break. The product of this reaction is an alkene.
It is important to remember that E2 reactions are always in competition with SN2 reactions. In an SN2 reaction, the base does a backside attack on the leaving group site, and then the base attaches to the carbon chain. To select for E2 reactions, you should use a strong bulky base, like tert butoxide. But if you want to favor SN2 reactions, you should use an unsterically hindered nucleophile, such as sodium hydroxide. The order of reactivity for E2 reactions favors sterically hindered sites. So tertiary carbons are favored over secondary carbons, which are favored over primary carbons. This is different than SN2 reactions where the opposite is true. Primary carbons are favored over secondary carbons, and SN2 reactions don't happen on tertiary carbons at all. The reason for this is that it's easier for a base to access a protic hydrogen than it is for a nucleophile to access the leaving group site.
This example shows how sterics are involved in E2 reactions. Here, methoxide cannot access the tertiary carbon that has a leaving group because it is so sterically hindered. Therefore, the SN2 reaction cannot happen. Instead, it attacks a protic hydrogen that is vicinal to the leaving group. This hydrogen is more available. The alkene product is formed.
E2 reactions follow Zaitsev's rule, which states that the most substituted alkene is favored.
In this example, tert butoxide is added to an alkyl halide. Tert butoxide attacks the protic hydrogen, which forms an alkene product.
However, in this reaction, another product called the Hoffman product is also formed. Steric hindrance of a base favors the Hoffman product because the hydrogens on the less substituted external carbons are easier to access.
For an E2 reaction to occur, the leaving group and vicinal hydrogen are most commonly in an anticoplanar orientation. This keeps the base far away from the leaving group. The alkane will rotate to the anticoplanar orientation because it produces the lowest energy transition state.
To recap, for E2 reactions, use a strong bulky base. Sterics help drive E2 reactions. It is a single concerted step and happens in the anticoplanar conformation. And then finally, Zaitsev products are favored.
By Shanae Asao,
Zach Strader,
And Corinne Pingle.